let us continue on in our examination of error terms. When we last left, we remember this wonderful little smile indicating positive autocorrelation. Now, let's look at the lagged error terms, where we compare error from one period to the error from the immediate previous period. Kind of gives us a better sense for, do we have positive auto or negative auto? This looks nice. You can kind of tell that it's probably positive auto correlated, but sometimes some of the relationships are a little sneakier than that. So we take our ETS annual revenue data, right? We run our regression like we did before, except now we will take the studentized residuals, and again, it doesn't matter which one you take really, and we lag it a term, i.e. period 2 becomes period 1, period 3 becomes period 2, t minus 1. Okay, so we've got our lag terms, and then we simply have to plot those lag terms. So we plot the lag terms, and we get something that looks like that. Now that, if we were to look at it from the regular scatter plot point of view, we'd say, hey, that's a slight positive relationship. Guess what? That corresponds to positive autocorrelation. Right? Very convenient, right? Just look at that. Go, oh, positive, and it's a little clearer, a little cleaner as to what the relationship is. So this is kind of nice to look at the error terms versus their lagged corresponding error term, because it really kind of pops out at us a little bit more strongly. So let's look at I have some more data, and then look at the This is Stantec looking at annual revenues versus employees. And so we're using the number of employees to predict annual revenue. Now, it's kind of interesting as to the nature of this relationship, because you could easily say maybe annual revenues is the X variable and employees is the Y variable. Maybe as revenue goes up, they hire more people, right? So the whole relationship between here is actually quite interesting, and it could be controversial. You could make an argument as to what the exact nature of this relationship is. So kind of cool that way. So we have it's a simple linear regression, so we have our R squared, very, very high, right? 97.5, let's call it 7% of the variation in annual revenue is explained by this model. The model is significant, and you're going, oh crap, but the graph's in the way. How do you know? Well, I can take a peekie, and I can look at the p-value for the sole intercept, and that's going to be the same p-value as for the significance f. And this only works for a simple linear regression. Don't start trying to do this in multiple linear regression, but it does work in a simple linear regression. So I can say, I don't know I can figure out the f-stat because I can just look at the ratio of these two mean squares here. But we see the p-value very small. Okay, so the model is significant. We have some precursor here, a Durbin-Watson test statistic popping out at us. Okay, VIF is 1 because there's only one independent variable, so there's no other independent variable for it to be related to, so that's kind of easy peasy, right? And so we know we can see there's a positive relationship here. Now we're going to look at the errors and zero in on the errors. Same procedure as we took before. Okay, so no difference here. Okay, do the same procedures we did before, and you can kind of see, okay, well, we plot the errors versus the ET versus ET minus 1. We see a negative relationship there. But look at that. When we plot it in our old-fashioned way with the time series plot, we see the sawtooth, right? And the sawtooth, we're up and then we're kind of down. Yeah, maybe that's less a tooth. Maybe it's a chipped tooth or a molar. But, it kind of goes up and then back down and then up and then down and then up. Okay. And so we see that sawtooth pattern, which we understand to be related to negative autocorrelation, but maybe a couple of these related errors here where we have a string of positives could make us doubt ourselves a little bit as to whether we indeed have negative autocorrelation. On the other hand, we could look at our graph and we can see, right, yeah, that looks pretty negative, right? And we go, okay, I'm feeling a little bit better about calling this a possibly negative autocorrelation. Okay? What is interesting, and this is what we get into the Durbin-Watson test statistic later, is look at look at the regression we see in the bottom corner here. Y equals to minus 0.6948x times by some intercept that we don't really care about. Okay? That's a negative relationship, negative autocorrelation. In fact, it's starting to get at the whole sense of what Durbin-Watson gets at. Right? They actually, behind the scenes, will do this kind of regression. And so we see a negative coefficient, negative autocorrelation. If this coefficient is significantly less than 0, then we'd say we have negative autocorrelation. If we were to do the similar regression, get a positive number, and we go, hey, we could just do a simple test, is that particular coefficient significantly greater than 0? And you have positive auto, right? Negative, less than 0, positive, greater than 0. Right? So it really comes down to some simple linear regressions used in all sorts of neat little ways, based on a formula for error, which is itself not very complicated. So, short little clip here. Let's jump into the Durbin-Watson test statistic in the next one.